Question 1. A pump is pumping 2 metres cubed a minute of water, the surface of which is 5 metres below the pump inlet. At the outlet, the pump has a diameter of 100 millimetres, and at this point the pressure is 8 bar. From the nozzle, which is at the same level as the pump outlet, the jet rises 35 metres. What's the problem? We want you to calculate the energy in kilograms per kilogram of the water. First of all, at the outlet of the pump, and secondly, at the top of the throw of the jet. So he's asking you to work out the energy per kilo of the water at the outlet of the pump at the top of the throw of the jet. And then I want to explain why 1 and 2 are not equal. So why are they not equal? And you've got to take acceleration due to gravity. It tells you in the question as 9.81 metres per second squared. What is the first thing I said to you to do? Draw a sketch. Draw a sketch. Look at this sketch here. This shows you here where the guy's working, where the jet is, where the datum is. The datum's got to be at the lowest point, sea level. Then you've got 5 metres above, you've got your pump. You put in your details, 2 metre cubed a minute, your diameter at the nozzle is 100 mil, 8 bar. Then you've got your nozzle, and you've got 35 metres, that's the jet height. So point A is where the pump is, point B is where the jet reaches at the top of that 35 metres. Point A and B. Let's work it out then. Now, first of all, this question deals with energy. Don't forget, potential energy is due to its position, kinetic energy is due to movement, and pressure energy is in the fluid. In this question, the energy is quoted in bars, pressure energy. So this is the formula to apply now. PA times 100,000 plus rho GHA plus half rho VA squared equals PB times 100,000 plus rho GHB plus half rho VB squared. Do you understand? Because we're using bars, this is the formula we've got to do. So now we know which formula to apply, we need to start working something out. So let's look at point A of the system. Point A is at the pump. Let's work out the energies at the pump and add them together. So at the pump, let's first of all work out the pressure energy. Now the pressure energy is P times 100,000, because it's quoted in bars, which gives you 800,000 joules per metre cubed. Don't forget per metre cubed. Now the question is asking you per kilo. Now 1 metre cubed is 1,000 kilos, so you divide it by 1,000. Do you understand? It's 800 joules per kilo. That's the first pressure energy at the pump. 800 joules. Now what's the potential energy per metre cubed? Well, this is rho GH. So if you substitute in rho GH, you get the density of water is 1,000 kilos per metre cubed, so it's 1,000 times 9.81 times, how high is it? The pump from the datum line, 5, gives you 49,050 joules. However, don't forget again, the question's asking you per kilo, not per metre cubed. You've got to divide it again by 1,000, back to 1,000, which gives you just over 49 joules. The next part of the question is asking for the energy again at the outlet, is the velocity energy. To work this out, we need to work out the velocity of the water. Don't forget what I said, a very important formula for Bernoulli's is the continuity equation, which is Q equals VA. And in this case, by transposition, we need to work out V. Now V is Q divided by A. Now first of all, convert. Don't forget the SI unit, the Systems International Unit of Flow, is metres cubed per second. The question gives you it in metres cubed a minute. You've got to divide it out. It's 2 metres cubed a minute. So if you divide that by 60, Q equals 0.033333. That's Q. Next, we need to determine the area of the outlet. Don't forget, the SI unit of area is metres squared. So how do you convert to area if you've got the diameter? Well, the formula to use is 0.7854 times d squared. This is a formula to work out the area when you know the diameter. Therefore, in this particular one, it's 0.7854 times it's 100 mil, which is 0.1 metre, times, so it's squared, 0.1 times 0.1. The area at the pump, area, is 0.007854 metres squared. So you know your Q, you know your area at the pump. Now you can work out V. So V equals Q divided by A. So V equals 0.3333 divided by 0.007854. It gives you 4.24 metres per second. That's what you need to work out. You need the velocity of the water at the pump so you can work out the velocity energy. So you've worked out the velocity of the water at the pump. At the pump, the velocity is 4.24 metres a second. Then all you do is you substitute in the formula, half rho V squared. This gives you a half times 1,000 times 4.24 squared, gives you 8,980 joules per metre cubed. Don't forget, the question's asking you energy per kilo, so all you do is you divide it by 1,000 and it gives you 8.98. Now, all you do now is you add the three energies up. You've worked them all out. The total energy at the pump is 50 plus your 800 plus your 8.98 gives you 858.98 joules. This is the energy per kilogram at the pump. That's the first part of the question. Now you need to determine the energy at the nozzle. Now, as you can see, all the energy is converted to potential energy. Because the water is going up the jet, at the top of the jet, where the water stops, can you see? All there is potential energy. It's water stopped. It's got as high as that. That's stopped. So there's no velocity at the top. There's only potential energy. So all the energy has been converted to potential energy. So at the second point, at point B, all you want to work out is now what is the potential energy of that water at the top of that jet? Because it's gone, that's it, there's nothing else. Well, all you do is you use this, the potential energy per metre cubed is rho GH. So you've got 1,000 times 9.81 times, now it's 35 metres from the datum line. Don't forget, 35 metres gives you 343,350 joules. However, again, the question's asking you per kilo. You divide it by 1,000, you get 343.35 joules. That's your answer. That is the potential energy of that water. Therefore, as you can see, the energies are not the same. At the pump, it's 858.98. At the jet, at the top of there, it's 343 approximately 5 joules per kilo. You've lost a lot of energy. Why? Why is this energy different? This is because of all the energy losses, such as you've got frictional loss through the hose, frictional loss in the nozzle, you've got losses due to turbulence in the nozzle, and friction and turbulence as the water travels through the air. Do you understand? Through the whole system, in this particular case, there's a lot of energy losses, and that's why you do have to take it into account, and that's why the energies are different at point A and point B, due to energy losses due to friction. And that is the completion of question 1.